Okay, ladies and gentlemen, this is the last of our Wednesday talks, but not least, of course. So I'd like to introduce Stefan Riezler, who he tells me is from Austria, which is a country in which my country used to be associated. He got his PhD, however, from Germany, from Tübingen, under Steve Abney, who was then there. And then he went for a short postdoc to Brown University, and then to Stuttgart, associated himself with Mats Roots, and has been in PARC for the last 4.5 years, working all this time mostly on parsing. But now he switched to translation. He said, unfortunately, but I assured him that we know from Dan that translation is just parsing. So he hasn't changed anything.
Well,
and we give to our speakers this.
Thank you very much. So, thanks for the invitation and thanks for the introduction. So I have to disagree with Dan. Machine translation is different from parsing. So some things are the same, but what's definitely different is the scale of the experiments you're doing, that's one big obstacle. The Wall Street Journal looks like a toy experiment to you once you work with these hundreds of thousands of parallel text. If you want to parse both sides and if you have to do, we have been working on that project for more than a year now. It's just 2 people, and we thought we should be able to do it in the summer because, it's just like parsing, but it's not. So, yeah. So the title of the talk is Revisiting Transfer-Based MT in a Phrase-Based SMT Framework. And so first I will talk about the stuff we could do successfully so far, namely automatically extracting F-structure snippets for transfer rule induction. So we have a technique to automatically learn the key component of the system lane with the transfer from source language parsers to target language parsers. And that works, and that's nice. And I will talk about the system components, which consist of a parser, transfer, and a generator, about a preliminary experimental evaluation, and about current and future work. So in our transfer-based machine translation has a long history, at least in Germany. So they had this very big project called Verbmobil, where several universities worked for a decade, basically, on a system which used deep processing, also syntax and semantics, and parsing and transfer and generation, and all the rules were crafted by hand. And the outcome of this, I would say, of this enterprise was, it was nice for the people to be able to do their own research with lots of money, but the machine translation system didn't work at all. Because it was just not possible to scale, even on this, the domain was dialogue, and writing rules by hand was just impossible. Unseen words, all the problems you have with parsings are exponentiated if you have parsers on both sides and if you have a transfer system in between. So every error you make in the source creates an error in the transfer, creates an error in the, it's just impossible. So our first obstacle was to find an automatic way to induce transfer rules from parallel corpora. And the problem you have to solve for is a coverage accuracy trade-off, as I would like to call it. So if you want to, so one example for statistical transfer-based machine translations is, for example, the Yamada Knight or the Eisner and Gildea systems, which use a stochastic context-free process to transfer a tree to a string or a tree to a tree. So you can look at that as a kind of a transfer system. And the advantage of a system like that is you have high coverage because you can all possible transformations of a source language tree into a target language tree are allowed. There are very few restrictions. And the work of Dan Gildia basically was to extend the power of this system, because you want to have transformations which are not, I mean, the first systems only had insertion, yield translation and reordering of the trees. And then introduced a technique which copied parts of trees, which he called, was not copying, cloning, right. So those systems have high coverage and efficient dynamic programming techniques because they work on context-free stochastic processes, but they have a sparse data problem and they have to respect linguistic constituent boundaries, which is one of the main advantages of the state-of-the-art phrase-based SMT systems, that they don't have to, that they are not restricted to linguistic constituent boundaries. So then from the other side, in an EBMT, approaches have been presented to automatically, I would like to say semi-automatically induce transfer rules by specifying licensing conditions which tell you, given a word alignment and given parallel trees, how you can extend a given alignment a given alignment for a small tree to a larger tree. So for example, one licensing condition tells you if in the source language you have a verb-object combination and the object is aligned to a verb in the target, then what you can induce from that is verb-object combination in source goes to verb in target. So that's one licensing condition which allows you to induce a transfer rule which transfer verb-object into verbs. But you have to write that down. And we basically found that it's not true that it's 20 or so licensing conditions are enough to get high coverage. You basically, for each example we looked at, we had to invent a new licensing rule. That didn't work for us. I mean, for other people maybe it worked, but Declan Groves and Andy Way had a paper last year at Coling where they also showed that this approach is highly accurate due to the manual guidance by licensing rules, but you have a problem of low coverage if you don't want to invest very much time into writing up these licensing rules, and linguistic constituent boundaries have to be respected. So phrase-based SMT, as you all know, avoids all of those problems by just avoiding linguistic structure. And phrases are simply defined as contiguous word sequences in a word-aligned corpus where the words in the source are aligned only with words in the target and vice versa. And the advantage of this simple non-linguistic phrase definition is that you get high coverage, efficient decoding if you use a beam search. You include local information about fluency by learning long snippets of phrases, and you can learn idiomatic expression which are not consistent with linguistic constituent boundaries. Then what we would like to have is a system which has all the advantages of the phrase-based SMT system and the precision of the standard parsing transfer generation systems. So our approach is a transfer rule induction algorithm that incorporates this idea of contiguous and mutually aligned phrases into the world of functional dependency structures, which is the kind of parses we work with in LFG. So you can think of it as dependency trees. So this gives us high coverage. We can learn transfer rules for F-structure snippets that don't correspond to linguistic constituents. But in addition, extending the phrase-based SMT model, what we can do is we can learn configurations that are local in the F structure but non-local in the string. So I will come back to that. So it should be possible to learn phrases for dislocated elements, for topicalized elements, which is important for languages like German, where you have lots of those things, where things which belong together are not adjacent in the string. So if you want to learn a phrase, you have to learn the phrase which includes all the words in between. And in F structures, those things are adjacent, so you can learn those.
I don't know what F structure is. What's F structure?
It's a dependency tree. So F means functional, and the functions are grammatical functions. So it's just an annotation of a context-free tree with labels indicating the grammatical functions of the constituents. So what we also can do is we can deploy the linguistic information we get from the parsers to filter the transfer rules. So we have an additional filter. So we don't have to learn all possible combinations of F-structure snippets going to F-structure snippets, but we can impose some linguistic restrictions which tell us, no, that's not a good transfer rule. And that the main point is that the goal is to automatically learn transfer rules which can feed into a standard linguistic generator which guarantees grammaticality. So that was the whole idea. And why did we go into machine translation? So our hope was that we have a bidirectional parser generator. Why don't we use that for machine translation and guarantee grammaticality? And first we have to get our transfer rules and then run it through the system and scale up. And well, as we will see in the experimental evaluation, we can show for the parts of the system that work, we can improve fluency and translational adequacy. But we have to back off in so many cases, so we have to introduce robustness techniques because the parser isn't good enough, the transfer isn't good enough, the generator isn't good enough, that all over the system falls down in comparison to a phrase-based system. So it's a lot of development which has to be done to get that system at the level where the phrase-based systems are at the moment. But if we invest that, then we will be better. But
sorry, Stefan, just a question of clarification. Are you trying to induce these alignments directly of the structure pairs, or are you trying to learn the relationships between constraints on the C structure nodes between?
No, it's just F structures. We never look at the C structure.
C structure is irrelevant.
Yeah, only the Fs. So I will give examples how we do that. So the requirements for extracting the snippets is, so we need a sentence-aligned bilingual corpus, automatic word alignment, and LFG grammars for source and target. And so grammars for several languages have been developed, so manually written grammars in the Pargram project, and we have grammars for English, German, Japanese, French, Norwegian, Chinese, Welsh, Urdu, and Arabic, listed in the order of their quality and of their size. Yeah. So we work with English and German at the moment because they have high coverage and they have been worked on for a long time. Japanese is also quite good, and Arabic we just started to work on.
And when you say grammars have been developed, I suppose you mean by hand, or
yeah, that
of a parse corpus?
No, I mean those. Okay, the Chinese grammar has been read off the Chinese tree bank. So our colleagues in Dublin developed a technique to read off LFG grammars from parsed corpora, similar to what Steve did for CCGs and stuff like that. And the German and English have been developed by hand. So it's a mix. And the English grammar, actually, there's also an English grammar read off the Penn tree bank is better than the handwritten English grammar, because the main reason is it's closer to the test set. So the handwritten grammar is just the upper bound of the handwritten grammar. So if you look at all possible outputs of the parser and choose the one which has the best match to the gold standard, then the upper bound is 85%. So the Wall Street Journal grammar for English, the LFG grammar, has an upper bound of 90%. So it's
yeah, but if you
whatever.
go
Yeah.
and tested them on some third neutral corpus, let's say English news file from somewhere else,
Yeah.
perhaps it would be equal.
Well, no, they're actually also on new domains. So they tested that on the BNC. They are also better on new domains. Yeah.
So we also have many more rules than you would have.
Yeah.
You know, like we've got 30,000 rules sometimes, whereas you wouldn't have 30,000 manually created rules.
No, I mean, the manually created English grammar also has 100% coverage, but in order to get the coverage, you have to introduce techniques which reduce the accuracy. And for a tree bank grammar, you get coverage for free by just throwing in all those rules. And a coverage for a manually written grammar means you have to back off to parse parts of the sentence correctly and then stitch them together in a right branching tree, for example, and you look for the smallest number of those chunks, and those parsers they are really bad because they mostly get the functional annotation wrong. The C structures are fine, but well, anyway, I just wanted to say that we have grammars for source and target, and we can read them off tree banks, so there is lots of room. If this machine translation project works out well, there's lots of room for us to extend to other languages, and we have grammars for languages where there are no tree banks, so I don't know if a Welsh or Urdu tree bank. And, yeah. And we have a bidirectional system for parsing and generation, which is the key. Yeah.
I don't know why you bother with anything but English and German. I mean, you just started out telling us how many difficulties you have.
Well,
why don't you stick to languages that you know?
Because
and you're not under duress from the government like we are, that we won't be financed.
That's not true.
Arabic and Chinese.
No, unfortunately, the new business strategy for PARC is that we have to apply for government funding, and the government doesn't care about German, so you have to do Arabic and Chinese.
Arabic's interesting anyway.
Yeah.
Sorry.
But to start off, it's easier for me if I can do German because I see what's going on. And
if you can first do a language that we actually know,
yeah.
some hope of doing a language that we don't know.
Is the generation component stochastic as well?
Not yet. That's what I'm working on at the moment. Yeah. So the procedure, we start off with an improved, which is now standard, improved bidirectional word alignment. You align in both directions, intersect and extend, parse, source, and target, and we select the F structures which are most similar in source and target according to a crossing brackets measure. So that's the F structures we use to read off the transfer rules. So that works much better than selecting an F structure here and selecting one there and then reading off the transfer rules from this possibly erroneously chosen stochastically selected F structures. Then we define many-to-many correspondences between the substructures of the F structures based on the word alignment, extract primitive transfer rules, and create all possible combinations of the basic rules and filter them according to contiguity and type matching constraints. So for example, if I have dafür bin ich zutiefst dankbar and then English translation, I have a deep appreciation for that, and many-to-many word alignment which aligns dafür to word 6 and 7, which is appreciation, deep appreciation, bin to have, ich to I, zutiefst to deep, add deep appreciation, dankbar to appreciation. So that's a wrong output of a many-to-many word alignment system. So some things are right, some things are wrong. And so what we first do is we project the word alignment onto the dependency structures. So can you read that?
I don't understand what you said. Dankbar goes with appreciation, right?
Yeah.
So why did you say it's wrong? Appreciation is the fifth word.
No, I think it goes
So-
with for that at least. I don't know how you're reading the.
No, dankbar means...
No, you can see it here. So the lines here indicate which predicate items are aligned in the F structure. And dankbar is aligned to appreciation, but appreciation is aligned to zutiefst dankbar, and zutiefst is aligned with add deep appreciation. So zutiefst shouldn't be aligned with add deep appreciation. It should be aligned with deep and not more. So some things are right, some things are not so right. So, but that's from this many-to-many word alignment, we get an alignment of the predicate values of the functional. So those are two F structures. That's the German F structure, which indicates the subject, and an X-comp. So X-comp is a constituent from which you can extract. So it's an embedded constituent. And that constituent has so it's dankbar with an adjunct dafür zutiefst. And here the structure is similar. You have a subject, but not an X-comp, but an object. and the object is a deep appreciation for that. So now you want to learn from that parallel.
I'm sorry,
Yeah.
Stefan, I don't understand what the criticism is. I also don't understand.
There's no criticism. I'm just giving an example.
I know,
Yeah.
I see that line. You made some argument, and I just didn't understand it. Why should thieves align with appreciation at all?
Because the automatic word aligner did that. So that's a real world example. So I'm just saying that's what we have to deal with. So we have errors in the word alignment. And even with errors in the word alignment and errors in the parsers, what kind of rules can we learn which tell us how to translate a sentence like that into a sentence like that?
Okay, excuse me. And the lines that you have from the German to the English in the T there.
Yeah, they are
obtained
from the word
they are
alignment.
sort of forced from the word of phrase-to-phrase alignment.
Right. Yeah.
I see. And you can't. Okay, and this method you just have to do this, right?
Well, that's
So far.
in the phrase-based, that's what you do. You have strings and strings. You have a matrix, and you have the word alignment, the many-to-many word alignment, and we just map this many-to-many word alignment into the F structures, and then we start reading of primitive rules, combining the primitive rules, and using some filters to filter out bad rules.
Okay. So what are the rules you'd extract from this?
So yeah, so the first rule is like a very simple rule which just translates the predicate ich to the predicate I, and that's variables. Then another rule.
And these are lexicalized rules.
Yeah.
Okay.
And that one here translates sign to have, but also translates the argument. So it takes the argument subject xcomp, goes to subject object. So the xcomp is translated in the object here. So then another primitive rule is dafür translates into for that. So you have to specify certain templates how you can read off primitive transfer rules from the word alignment. So and one of the templates is that you can take the arguments with you and the embedded predicates of the arguments.
And X2 is not specified, but you'll insist that something be there.
Yeah. So I just know for has an object which I don't know what it is, and the predicate is of is that right?
I don't understand.
No, that should be. I think that should be an X2 here. Yeah.
Yeah, exactly.
Yeah.
Shouldn't that be the
Yeah.
is for that?
Yeah. Yeah. It's yeah. Sorry, that's
Okay. Let's look at the tree for a minute.
Yeah.
To understand how you got this. Yeah. So, okay. For that. Okay.
yeah. The predicate of the object is that.
Yeah.
So and it should be
X to that.
yeah. Okay, so that's how we learn the primitive rules, and then we build complex rules by combining all the primitive rules. So for example, if we look just at the pred values, then we combine sign to tiefs dankbar to have a deep appreciation. So we had a rule for sign. Well, I didn't show that to tiefs dankbar, but so if we have a rule for sign and one for zutiefst dankbar, one for have and a deep appreciation, then we combine it. Then we can combine one with sign zutiefst dankbar dafür, have a deep appreciation for that, sign ich zutiefst dankbar dafür, have I a deep appreciation for that, and so on. And the filters we use to weed out illegal combinations.
So where do you get this? This is generation now?
No, this is just the primitive rules I showed before are now combined. All possible primitive rules are combined. So if you look at this example here, I have a rule which translates sign to have, a rule which translates ich to I, one which translates dankbar in a deep appreciation, and I can combine that now into sein ich, I have, or sein ich dankbar, I have a deep appreciation. Sein ich dankbar dafür, have I a deep appreciation for that, and so on, right? But there are certain filters which tell me which of those combinations are not possible, because if you have big F structures, then you have to create an exponential number of such mappings, and it would be nice if we had some idea of which combinations are legal and which are not.
You really do throw the functional information away at that stage.
At that stage, right. But it's coming back. No, it's not string to string, it's primitive rules combined. I'm just showing the strings because it would be unreadable if I, yeah.
Let me ask you a question. Go back to your previous one for a minute. So if you only done a partial compiling out of the rules, would these still look like these F structures with much longer?
Uh-huh.
So it could be a whole phrase with a hole in it, and then the corresponding phrase over there with a hole in its place.
Right, yeah. It would basically, so sein ich would be, what you see on top here, yeah, and goes to that here.
So it would be have I with of.
Yeah. Mm-hmm. So, and the first constraint is similar to the constraint people use in phrase-based SMT, which we call transfer contiguity constraint, and that tells us that you can learn a transfer rule only from F structures where source and target F structures each are connected, and the F structure in the transfer source can only be aligned with F structures in the transfer target and vice versa. So connected corresponds to adjacent in the string. So the condition you have in phrase-based SMT is that the phrases have to be adjacent words. And for us it's connected F structure. And connected F structure mean you have to be able you have to be able to go up, and so for example I and a appreciation is connected because you can go up to the subject and down to I. So if you can't do that, if you can't pick a grammatical function where you, as top node which connects the lexical elements, then the F structure is not connected. And the other condition is the alignment has to be mutual. So the F structures in the source can only be aligned with F structures in the target and vice versa. So an example for that is this constraint, so that the mutual alignment tells us that a translation of dankbar into appreciation is not possible in our world, since appreciation is also aligned to tiefst. You see, appreciation is aligned to tiefst and dankbar, so we can't learn a rule which translates dankbar into appreciation, because you would have to include tiefst and all of the rest as well. So that's exactly the same as the phrase-based SMT constraint to do that. Then
furthermore, you will have many sentences in which dankbar is thankful, right? I mean, ich bin dankbar, I am thankful. And so that will be all confusing, right? It's only because the dankbar is sort of at the end here.
Well, it's basically a means to deal with wrong alignments and wrong parsers.
Right.
So if you have dankbar aligned to thankful, then you're fine. I mean, yeah. So this
I am just pointing out that dankbar does not always present difficulties. It is the fact that it can be translated in many ways that gives you.
Right. So it's basically the errors we have in our training data which make it necessary to do that. So what I want to say is that this transfer contiguity constraint looks very restrictive, but it still allows us to learn idioms like skip, there is, from configurations that are local in an F structure but non-local in a string. So for example, we could learn, if we have a sentence es scheint with something in between to geben, then we can learn there seems to be. we can learn that. Even so, the things in between don't bother us, because if the things are local in the F structure, and if A shine is aligned to their seams, and 2B is aligned to zugeben, then we can translate that, and this transfer contiguity constraint doesn't interfere, and that's important. I mean, it's important to make the point that we can do that. I don't have an empirical proof that this is what gives us the advantage of the over phrase-based systems. Then what's interesting also is that now the F structure information comes back via linguistic filters on the transfer rules. So first what we do is our pred values are morphologically stamped. So our alignment is not between full forms, but between morphologically stamped values, which in theory should give you generalization power, because you're now looking at stems. Then what we can also do optionally is filter F structure snippets based on the consistency of their linguistic categories. So for example, in the string-based world, we could extract a snippet which aligns to Thief's dankbar into a deep appreciation. But in our world, we can filter that out if we want to by looking at the linguistic type and see that to Thief's dankbar is type adjectival and the deep appreciation is type nominal, so they don't match. And you don't want to translate an adjective into a nominal type. But if you see that you're losing coverage by doing so, then you shouldn't do it. But it improves accuracy in doing that, because the generator then won't have to deal with nominal types where he expects adjectival types, and he doesn't have to back off to some robustness techniques to deal with unknown combinations and stuff. So and also a translation of sign to have could be discarded because sign, the arguments of sign have type adjectival versus the arguments of have type nominal. That might be really too restrictive, because otherwise, I mean, if we would do that, then we couldn't learn the basic transfer rule which translates sign to have, which is necessary to translate this example. But that's another thing you could do. If you apply all these linguistic filters, then what you basically end up is that you learn very large phrases. So because if you extend the size of your phrases, you will always find a matching type. For example, sign zu tiefst dankbar can be translated into have a deep appreciation, because now we have a verb type here and a verb type here. So now it's fine again. And if you
say again, why is it fine?
Because sein zutiefst dankbar and have a deep appreciation are both verbs, so verb phrases. So the types match again, and you can learn the translation. And here you had a mismatch because sign and have different types of arguments, and that would create a mismatch. But here you just look at the verb phrase and yeah.
Yeah, just my German is really bad, so I was kind of lost the point earlier. So is literally the German means be deeply thankful, and it's being translated as have a deep appreciation?
Yeah.
Okay, so it's actually the verb to be. Okay.
Yeah. So it's the argument structure of the verb which is mismatching here. So it's.
So this is kind of similar to the Spanish examples of I am hungry versus I have a hunger.
Yeah. Yeah. Mm-hmm.
It's actually an awful translation, isn't it?
Which one?
I mean, I have a deep appreciation doesn't mean I'm deeply grateful in English.
Thankful. But
I don't think it means the same thing.
Yeah. Well, but that's another thing you have to deal with. I mean, these translations are not very literal. So we work with the Europal data, and they are really not literal at all, those translations. They are nice translations, but okay. So the full system should look like that. So we parse the source and create packed F structures, feed them into the transfer, which creates packed F structures again, translated F structures. Then we do a stochastic selection and generate and produce the target. And the nice thing about this packing all the way through is that you don't lose any information. You can use dynamic programming all the way through, but in the prototype system at the moment we don't use packing here, we only use it here. And that's creating some problems already. So looking only at one German parse, and you know that the German parser isn't as good as it could be, creates errors right from the start. And so, well, anyway, so that's how it will look like when we're done with fixing everything. So the parser is an LFG parser producing constituent structures, context-free trees, and functional structures, which are labeled dependency graphs encoding predicate-argument relations, and we only work with the F structures in parsing, in transfer. Then the parser produces a packed parse forest, and we have stochastic disambiguation techniques which can be applied to all of our grammars, and the grammars can be fed, well, they work with the same so-called XLE system, which has, they use the same techniques for producing packed forest. They can train with the same discriminative log linear model, and they can basically actually also use the same features. And that's another thing I'm just working on, retraining the German grammar, because we didn't have its stochastic disambiguation trained for the German grammar, and that's what we need. Then what we also have is tokenization and morphological analysis via a cascade of finite state transducers. And they are not weighted finite state transducers, it's just they produce ambiguity and deliver the ambiguous tokens and morphological analysis to the parser, and the parser disambiguates them. And the grammar have 100% coverage, and 80% of the coverage is good parsers, no problems, and 20% are examples where we have to back off to what we call a fragment grammar. And what that does is, if you have unknown words or unknown combinations, then the grammar parses the parts it can parse correctly and produces nice F structures for those parts and stitches the F structures together in a sequence of right branching chunks and looks for the sequence with the smallest number of chunks, and that's the parse you get.
A question about the second bullet, is that C structure or F structure, the packed parse forest?
Both.
But you just said that you actually don't have a packed F structure forest.
No, we have, we could have, so for the experiment I will present the results for, we don't use packed F structures as output of parsing. We just use the first parse of the German grammar because we don't have a stochastic model trained for the German grammar. And it's important to have the stochastic model, because what we want to do is we want to create an n-best list in packed form. We don't want to look at all of them. We want to create packed representations, but not for, say, the first 200-300 parsers. And if you do good dynamic programming on the n-best list, then that's really, it's compact, good information. And we could have it in theory, but we don't have it at the moment because I'm just working on it. Parsing, transfer. So the transfer system applies rules in parallel in a non-deterministic fashion. Each fact, so fact means F structure snippet must be transferred by exactly one rule. We have a default rule which transfers any fact as itself, and the generator then does something to it if this default rule applies, so I will talk about that later. And what's nice about the transfer, it uses the unification and packing mechanism the parser uses. So it produces a packed representation of transferred F structures. So it can be done efficiently. And on this packed representation, we can do Viterbi decoding to find the best F structure. And at the moment, the probabilities are estimated just by relative frequency of transfer rules. So we count in the corpus what the relative frequency of F structure for English given F structure for German is, by summing up over all our German to English transfer rules and dividing by that.
So the sum should be in the denominator.
Some should be in the
There's some should be yeah, right.
Okay.
That would
Let me
be,
ask you a question.
yeah.
So here you're using the raw count of that structure, the FSF to FSE, based on this extraction of these structures followed by value filtering. And when you started that process, you had a single tree for the, let's say, the German sentence and a single tree for the English sentence, produced by monolingual parsers. And of course, they have to reconcile themselves to the word alignment, and so many things will not align. And in other words, many sentences you will not get all the pieces out of it that you could have because the parse structure doesn't align with it, doesn't reconcile with the word alignment. You could, in principle, have produced a endless list of parses on either side, and then given weights to the counts in the numerator based on the probability of the parse. That way you'd extract more out of every sentence pair. And then you could be aggressive in your filtering, meaning be very generous in hypothesizing transfer rules, and then be aggressive in filtering them out. Because it's possible that some structure is the second most probable parse in many, many sentences.
Mhm.
So that overall it has a high count, but if you only took the best parse, it never shows up.
Yeah, that's a good idea.
Okay.
Yeah, we didn't do that, but we will do it.
Okay.
So generation, we can use the same grammar for parsing the training data and for generation in translation. And what we had to do to our generator, we had to make it fault tolerant in the cases where the transfer system operates either on a fragment parse or produces non-valid F structure on its own. And so robust generation has to work on unknown predicates and unknown F structures. So generation from unknown predicates means, for example, if for example the German word Hunde is analyzed and stamped to the pred Hund and numerous plural, but we don't have a translation for Hund, so we don't have a transfer rule, so we translate Hund into Hund. What the generator does to it, it takes the German word and inflects it with the default English morphology, and what we get is Hunds. So that's useful for debugging, because people who don't speak the source language see what's going on. What would that be? Or they see it's a plural noun, and they can go back into the transfer rules or into the grammar and look at what's wrong with our plural nouns. And sometimes we are lucky and we get the right thing. Then generation from unknown constructions is more difficult. So what we have to do here is we have to add components to the grammar which allow to generate any attribute in any order. And we add that in as a suboptimal option into the standard English grammar. So for example, if a subject cannot be generated as a sentence initial NP, which is the standard rule the generator knows, so subjects go as sentence initial NPs. If that's not possible, the generator tries to generate it in any position as any other category. So that increases the ambiguity, and that's where we have to introduce stochastics to filter. I mean, to extend the possibilities and then to filter to increase the accuracy. And that's the biggest problem actually at the moment, that this robust generation really decreases the accuracy so much that overall the system is crappy, really crappy. Only in the cases where we don't have to do that, system is fine.
What do you mean by robust generation here? That means that it generates something, or that it generates a fluent thing, but it is not a translation?
No, robust means it generates something for any input. It's not necessary.
Fluent?
No.
No, not even that.
No.
So when you say accuracy, it's both not fluent and it does not represent
Yeah.
the source.
So I was going to say, you couldn't back off to a standard phrase-based system
Well,
just for that channel.
What we could do right now is just say we do translation by first trying our system, and our system tells us when it has to back off to robustness techniques in parsing or in generation. And if we have to do that, we just use the phrase-based system, and then overall we get a better hybrid system. But that's somehow boring, right? I mean, you want to build a full system end to end, not.
Yeah, no, I guess one of the things I'm thinking is that one way to get the robustness within your framework is to have lots of little rules which just take care of one word with its little tag on top. And if you covered all of those, of course you would have too many possibilities to search, but you could somehow disprefer them over bigger F structures.
Yeah.
And this again goes back to your extraction of the F structures. If you covered all your sentences, then you'd have these tiny one-word
Yeah.
F structure transfer.
Well, I know that in all components we have to extend the number of possibilities and then use stochastic filtering. And we only do it in the transfer part at the moment, and we do it not very good. We do this relative frequency counting without smoothing, so it's just, we have to do it for transfer rule induction, for the German grammar. We have to work on n-best lists coming in from the German grammar into transfer. Then we have to look. So what we also do at the moment is we generate from the best transferred F structure. We should generate from the n-best transferred F structures and then look at all the strings, and this will come. I mean, that's well, generation is the key problem for development. That's what we have to develop better. And the key conceptual problem at the moment is that we choose an F structure without knowing what the string looks like that it can generate, and that really that decreases our Bleu and NIST scores, because if you want to be good on those scores, you have to have all the information you can get about the reference translations. And generating from F structures produces, if the F structures are good, nice grammatical fluent strings which can be totally different than the reference translations, and Bleu and NIST score just fall down. You have to know what the word order in the reference translations is in order to fare well on. Yeah.
So let me ask another question about this unknown construction. So what's happening, I suppose, is that you produce your one best parse of the test sentence.
Yeah.
And then when it goes to the transfer, this rule probably uses that identity mapping that you mentioned.
Yeah.
Is that what happens here?
Here?
Yes. I mean, and then when it comes to the generation, you realize that it's a structure for which no transfer is available.
Yeah.
And so I guess one other strategy, if you didn't want to work on, if I didn't want to work on generation, I would say, okay, give me the next best parse and keep going until I don't have to use the identity rule at all.
Yeah. When it would also help if you had more transfer rules which are learned. Yeah. But in principle, this idea to insert parts you can't generate in their right position, in any other position, and try out other categories, it works fine. But you have to do some machine learning to choose between the options here, and that's not done at the moment.
So you're saying that in your candidates that you generate, there are really good candidates. If only
Yeah, I know that the Oracle is fine, so it's.
Okay, so maybe then you should work on generation.
Yeah. So to the experiment, so we worked in German to English using the Europal dataset, and we restricted ourselves for quick turnaround to sentences of length 5 to 15, which resulted in a training set of 160,000 sentences, development of 1,900, test of 1755. That's the same test set that was used in Köhn et al. 2 years ago. And if you now, in 2005, report results on that test set, people don't like it anymore. So it's that's old. You have to use new, larger test sets, and you can't restrict yourselves to lengths 5 to 15. That's out. I mean, that immediately tells people that your system is not good enough. The reason why you work on 5 to 15 words is because you can't do better, not just out of convenience. And well, we didn't. I don't know if we can scale up easily or not. I mean, we just want to get the system, all components done right on these 5 to 15 words. Okay. So what we do is, first we create this bidirectional improved alignment. Then we parse the training data, German and English. As I said, 100% coverage, 80% full passes, 20% fragments. We extract around 700,000 transfer rules. The current prototype transfers German, the first German parse, so it doesn't use an n-best list of German parses, which we will do. Then we use Viterbi decoding with respect to relative frequencies and generate from this one selected F structure, which we will also change by generating from the n-best F structures and looking, weighting the generated strings from the n-best F structures with an n-gram model. Not just the string which is created from the best F structure. Then we did a manual evaluation in order to separate fluency and translational adequacy. And we did that by randomly selecting 100 sentences from the test set and compared our results against IBM Model 4 as produced by Giza and the phrase-based system described in Köhn et al. With relative frequency weighting. So the system Philip gives away now is more sophisticated, so it uses relative frequencies and lexical probabilities and word penalty, phrase penalty, language model probability, and does a minimum error rate re-ranking for those 8 weights. But we compared ourselves against this relative frequency model because that's what we do at the moment. And we use the SRI language model and the Faro decoder. So in terms of robustness, in 55 out of 100 cases we had to back off to robustness techniques. In 15 cases this was caused by fragment parses of the German grammar, and the 40 cases had full German parses, but the generator had to back off to robustness techniques. And in 5 cases, the generator just didn't produce any output. So in the evaluation, we will split out this fragment and non-fragment examples, and the average sentence length on the fragment examples is 10.7, and in the non-fragment examples is 8. So the examples where we had to back off are slightly longer than the examples where we didn't have to back off. But it's not like that those examples are just 5, 6, and the other ones are. So, and what's also interesting, all systems had problems with these examples, which we call the fragment examples. So they are harder to translate in a way. So the manual evaluation was done by presenting the 3 system outputs and the human reference and the source sentence in random order to 2 judges, and the judges were asked to separately indicate fluency and translational quality on a scale from 1 to 5, where 1 is bad and 5 is good. And then we just averaged. So in what the evaluation shows is that overall, our system, which is the LFG-based SMT system, has a higher score than phrase-based and Model 4. But if you look at non-fragment and fragment examples, you see that all the gain we get, so that's a fluency, evaluation of fluency, all the gain we get is on non-fragment examples. It's 4.8 versus 4 and 4.4 for phrase-based and Model 4. But on the fragment examples, we are worse than all the other systems. So we have a score of 3.3 versus 3.5 and 3.4. But luckily overall, on this manual evaluation of fluency, we just beat them. And what's also interesting, the fluency is...
Five, that means these are 5 sentences?
No, that's the human, that's the manually created reference translation. That's the score, the 2 judges assigned to the human, to the manually created reference, and they were all fluent. 5 means they are perfectly fluent. Well, it's not surprising, right? I mean,
We were kind of judges because I guess I would find problems with human translations.
yeah, but the problems are not fluency problems. The problems are in does the translation convey the exact information which is seen in the source sentence? And that's so the next evaluation is on translational adequacy. And here the human doesn't get 5; it gets 4.77 or whatever. So on that measure, with respect to that criterion, we are worse than the phrase-based model, but better than model 4. And again, all the gain we get is on the non-fragment examples. And on the fragment examples, we are just a little bit better than model 4.
Low number is good.
High is
High
good.
is good. Oh, I see, okay.
So these are like average scores between the 2 judges?
Yeah. And the judge, also, I don't have the numbers for inter-judge agreement, but they were very close.
Excuse me, where is the model? Model 4, how am I to read the model 4 column?
So that means on all examples, model 4 has a worse score in term for translational adequacy than the phrase-based system and then the LFG-based system. And on non-fragment examples, on
45 out of the 100.
yeah. No.
No, 45 you have to go to robustness.
Yeah, that's something different. Yeah. So that's 3.54 means on a scale from 1 to 5 we get 3.5. Yeah.
And I was thinking about how many examples, like what fraction of all is non-frag and what fraction of all is...
Oh, that's right. The non-fragment is 45 and that's 55. Yeah. So on examples where our system didn't have to back off to robustness techniques, the numbers are like that. And on examples where our system had to back off to robustness techniques, that's the scores we get. And we did that to see what I mean. That's basically a first step to error analysis. We wanted to see where do we make the most errors, and we see when we have to back off to robust generation. So that's really what we don't do.
This means your technique is fine. Yes, get a good test.
Well,
One option is when you back up, when you realize in the process that you need to back up, just go and use Philip Gold's system instead of yours.
well, that's what I said. We could use but that's not what we want to do. It's somehow it's no longer research. I mean, maybe we have to do that. If some well, I don't think that even the government wants to fund a system like that. So I mean, they fund development at the moment, but it should at least look like research. And our
But there's a difference, though, because you just have a more robust backup, and
Yeah.
overall you would do better, even more than what you're doing now for the overall. So I don't think that's that bad.
Yeah.
It's an interesting, another column to present to say, like, if you did that, how about?
yeah, we should do that. Yeah.
So what you really need is you need a better LFG fragment grammar. That's what you need.
The generator is more the problem, not the grammar. Yeah, both, but it's mostly the generator. Yeah.
There's been a fair amount of research on stochastic generation, so I would guess that you can get gains pretty quickly just applying sort of
Yeah.
some stuff that's been done and then do more research into LFG specific issues.
Yeah. So, okay, so what I conclude from this manual evaluation is that a parse transfer generation system using this automatic rule induction framework can considerably improve fluency and also translational adequacy unless the system has to back off to robustness techniques. And overall improved results are to be expected from further developments of the system components. So currently I call our system a Fiat system. So Fiat in Germany, in German stands for Fehler in allen Teilen, which literally is error in all parts. So in English sometimes it's translated as failure in automotive technology, or fix it again, Tony. So we know what's wrong, so every single part is just wrong, and we have to fix the generator, the parser, the transfer induction, and then we will do better, because then we can improve the number of cases where we don't have to back off, and we know that we do already quite well in those cases. So I also computed NIST scores for the manual.
Excuse me, several. Is this on the 5 to 15 word sentence?
Yeah.
This is on the 5 to 15.
Yeah. Well, it might look different on longer sentences.
Yes, yes.
Yeah. So, and the NIST scores for these 100 sentences look like that. We are close to, on the non-fragment examples, we are close to the phrase-based system and better than Model 4, but overall, since we are so bad on the fragment examples, we are losing overall against phrase-based SMT and Model 4. So that's really discouraging. And the conceptual problem here is that if you look at the output of the non-fragment examples, the translations all are fine. They are all fluent and they have the right, they're adequate, but they don't match the reference translation, because we make this error that we choose an F structure and then generate from it. And that the generation possibilities are only ranked by the N-gram model, which knows a little bit about the reference translations, but not enough. So we should know more about the reference translations in choosing after transfer. And that's another thing that problem can be alleviated by not choosing one F structure, but choosing N-best F structures, generating all strings from the N-best F structures, and then including the N-gram score, the F structure score, and doing what everybody else does. So split up your system in a sequence of modules and assign lambda values to them and train them by minimum error rate re-ranking, and you will see this will improve even our scores. And so that's significance testing for the NIST scores on the 100 sentences, and not significant comparisons are clustered together, and we see that on the non-fragment examples all the systems are the same, and the division is basically between phrase-based and the rest, which is very discouraging. But what we can do here is we can do the same NIST comparison on a larger test set, and then all system comparisons become significant again if you increase the test set, and we get the same rankings, the same relations. So that can be done for NIST score, but it's not possible to do the same for the manual evaluation. So in order to make the manual evaluation significant, we would have to look at 2,000 sentences or something like that and do a manual evaluation. Or we should find a measure which makes it possible to discern fluency from translational adequacy in automatic evaluation, and we don't have that. So what we conclude from this NIST evaluation is that 100 examples is not enough, and statistical significance can be gained by scaling up to a larger test set, but from manual evaluation, not so easy. Then what we also see that NIST gives more credit to correct lexical choice instead of word order, and corresponds rather to the evaluation of translational adequacy than to the evaluation of fluency. So if you compare the NIST scores to the manual fluency and manual translational adequacy results. And what we also see is that the NIST score is much harsher than the manual evaluation, and the reason for that is that we think that we can produce good translations which have a low NIST score. Even so, it's not necessarily true that a good translation has a high NIST score. even if the reverse is true. So if you have a high NIST score, you have a good translation, but not vice versa. So for example, so the human reference is address by Mr. Kostunica, President of the Federal Republic of Yugoslavia. And the phrase-based system translates it directly, and our system translates it as address of Honorable Kostunica, President of the Federal Republic, which is fine. I mean,
Where did it get this honor?
well, that's somewhere in the training set, somebody must have said honorable for Mr. Kostunica. I mean, they have different ways to address the speakers, and one way to address them is honorable. And the language model liked it, the F-structure transfer rules liked it, and it's fine, but it doesn't match the reference translation, and the NIST score drops by 2 points. And the same for thank you, which we translate as thanks to Mr. or thank you, Commissioner Liikanen. We say thanks to Commissioner Liikanen, and we lose a lot because we don't have the comma, and and things like that. We have to fix things like that. I mean, it's stupid things, but you have to do it if you want to improve your NIST score. If you improve the NIST score, you will also improve your translations. Well, I don't say we have to go in there by hand. That's not and fix the rule, so to get thank you, comma. But we have to find techniques which do that. Then sometimes the errors we make are penalized harder than errors other systems make. So, for example, the LFG system translates we will win into we have won. So it gets the tense wrong, and so it loses 2 matching words. Whereas the phrase-based system doesn't know the translation for win and says we will siegen and gets a much higher NIST score. So I mean, not knowing the word is much better than getting the tense wrong. And so getting the tense wrong for us means that the generator produces those possibilities. So it's all the present tense F structure, all the strings which can produce from present tense F structure. We have been winning, we are winning, we have won, we win. And it makes the worst choice. I mean,
The right one is not there, isn't it, right?
no, it's not there. But I mean, I'm saying we make a mistake, but we win would have been better than we have won. Yeah.
Why are these options for present tense F structure?
Well, that's present perfect. That's progressive. Well, I don't know. That's LFG. That's.
No, but I mean the present perfect is not present.
It's a present tense.
Well, that's weird.
Yeah. Don't ask me. I don't. Yeah.
Is this learned or is this?
No, that's the grammar.
I think I would change the grammar.
What was the German tense?
Wir werden siegen. It's future tense.
It was future.
Yeah. Then.
So I'm sorry, I don't get this. So what is your explanation why you changed the future to past?
But that we make an error by not recognizing that we should translate future tense, but
you did not notice that wir werden siegen is future. You
but
didn't even, the analysis did not come up with that.
Right. But what we knew is that siegen is win,
Yes.
and all we got wrong is the tense. But
All you got wrong is not, you're putting it low. You're minimizing it, but if it's a question of information, then it tells you that you have won, I think Germany won First, Second World War. I mean, I don't know.
well. No, we are talking about the NIST score here, not about.
No, I know, but you are attached to this score, but the fact is that in this particular case, test is very important.
Okay. So I don't want to say that we do everything right and our errors are just minimal and we shouldn't get penalized for that. Sometimes using a parser is maybe not the right thing to do. For example, for strings like question number 5 by age, whatever, I mean, they appear a lot, those headers, they are in the training set. The parser is confused and backs off to, produces a bad F structure. The generator has to back off and inserts a what here, and the parser, well, and number 5 is, well, it's just, you see, I mean, things like that should just be recorded as is, as a phrase, as a string-based phrase, and translated without any changes. And we can do that by including multi-word expressions in the parser, by named entity recognizing and including lists of multi-word expressions which are not analyzed at all. And then we can learn transfer rules. Multi-word expression goes to multi-word expression, and we should do that. And here as well, so for example, Mr. Gräfe zu Baringdorf is parsed, so it's not recognized as a name, and the zu Baringdorf is thanks to Baringdorf, Mr. Gräfe. It's just messed up. Everything is messed up by parsing, by doing the right thing. Zu Baringdorf is to Baringdorf, but, well, you're not matching the reference translation.
Gräfe zu Baringdorf und etc. I mean, this is his noble title?
Yeah.
Yeah.
So if we compare our work to EBMT, for example, what I mentioned before, to Meneses and Richardson's work, or to Grove's and Andy Wei's work, then so in their framework, there is an automatic way to induce transfer rules, but you have to write the licensing conditions by hand. So that's a crucial step. Even if you have to write only a small number of such rules, you have to do it for every language pair anew, and I don't see how you can, well, get large coverage with those systems. And that's what people report, that they have coverage problems in their EBMT systems. Then another related work is dependency tree-led translation. So Dekang Lin and Chris Quirk and other people at Microsoft presented stuff at this year's ACL, and they work on unlabeled dependency trees, and they use parsers only for the source side. And the main difference is, well, the first difference is parsing only on the source side, which might be an advantage because they don't have to create target language parsers for all language pairs. But they don't use a linguistic generator, which we believe can improve fluency, and the whole setup can improve translational adequacy. But what they do is, and what we also should do and integrate in our system, they have a very refined lexical ordering model, which gives them all of the gain. So if you look at their system, it appears that most of the gain over the phrase-based SMT system, and they can beat the phrase-based SMT system. They are the first ones to show that they can devise a parsing-based translation system which beats the phrase-based system. So the gain is not in using parsers and linguistic information, but it's using the linguistic information in the ordering model. So lexicalize the ordering model. So use grammatical functions and lexical items to learn information about how to reorder the phrases which come out of their phrase-based system. Yeah. And they use a minimum error rate training of the system components. Then work which is closest to our approach is Ding and Palmer's approach. They also use label dependency graphs for source and target, and their approach to induce transfer rules is top-down. So what they do is they break parallel dependency trees into phrase-level dependency treelets by synchronous tree partitions. And they use a probability model at each node which tell them, is this a good place to break the parallel trees into smaller treelets, as they call it, and then from the treelets they learn transfer rules. Treelet goes to treelet. So it's top-down versus our approach is bottom-up, and they arrive at a similar induction algorithm. And they do minimum error rate training, and don't use a linguistic generator, but a synchronous dependency insertion grammar.
Is this Wasserbaum?
Yeah.
This is the guy who was here in the workshop 2 years ago.
So that's very good work. Yeah.
Well, you would have had one competitor less.
So the only difference between his approach and our approach is that he doesn't use as much linguistic information in filtering. His filtering all is soft filtering. So he has probability models. For example, this type matching we have, he has a feature which knows about types, and if the types match, then the feature gets a higher value. If they don't match, then not, and things like that. And that might be another way to increase the space of possibilities for our models. Okay, so current and future works. First of all, we have to do fixes to the Fiat system by n-best parsing instead of choosing the first parse. Scale up the transfer rule induction from 5 to 15 words to the full Europal dataset. Then we want to generate from n-best transferred F structures, not just from the best F structure. Then we want to do split the system into components and learn weights for the system components, either by using our log linear model or by minimum error rate training. And then what I'm doing at the moment is working on stochastic generation to increase the accuracy of the robust generator. And that's about it. Thank you very much.
Question? I think we already asked them.
So another,
So, but
yeah.
you actually, I mean, I asked you this question, why not stick to German? And you answered in some way, but actually you are sticking to German. Is that
Yeah.
right? All right. So what with the other languages?
Well,
I mean, if you have this trouble with German, right, you're certainly going to have it with Arabic or Chinese.
I mean, the idea is that the system should be applicable to any languages once you have the grammars for both languages.
20
And
years
it's
from now.
nah. I mean,
Well, look,
we will see.
We started doing a translation at IBM in something like 1986. So it's now 20 years almost. So, you know, 20 years is a short time. You got to be realistic. It's a very difficult problem.
well,
And we tried something simple, right? We did English with French. English and German is more difficult.
well, I mean, a group in Norway is working on Norwegian to English translation, and our colleagues in Japan, they are getting ready for translation. And if we have enough manpower and their grammars are good and the grammars are all, I mean, so this Paragram group has they meet every 6 months, and they make sure that the grammars have the same, well, there are certain general, well, it's basically a specification how to write the grammar. So it's not allowed to introduce new category or label names without asking the whole committee, is this approved? And certain constructions have to be treated the same way. So the grammars are really nicely parallel. It should be possible to apply the system.
But,
yeah.
people write grammars.
Yeah.
Sounds like it would take 20 years to do just
People write grammars. I mean, certainly when I studied IBM, which is 72, people were writing grammars already, right? And now it's, what, 30 years later, or maybe more, I can't even count well. And of course, nobody has yet written a decent grammar, or even of English.
Well, I don't.
I'm not attacking it. I'm just saying, honestly, page.
I mean, our handwritten English grammar passes the Wall Street Journal and gets good results. It passes as fast as Collins parser. I don't know what's the problem. You can do it.
Well, I actually did. I have a colleague, and she thought that the grammars are no good, and I was at that time, 2 years ago, optimistic that grammars are right. So we went to the Baltimore Sun and picked up 4 sentences and submitted it went to all parsers, meaning to Collins, Roots, etc. And they all got all 4 wrong.
At the sentence level, there was at least one error.
Yeah, well, it just was wrong interpretation. You know, the crossing brackets seems to be maybe 90% or 91%.
Yeah.
But it's just not good enough.
So this won't work for evaluating your own systems, but it strikes me that one potential automatic way to evaluate fluency would be to apply your parser to the English output of, say, another system. And since yours is not like a tree bank parser, that it will choke on disfluent strings, or a large number of disfluent strings, that in fact, whether or not something can be parsed by your LFG grammar is an automatic way to evaluate the fluency. Presumably, if it can be parsed, it's more fluent than something that can't be parsed.
Well, it's nice to hear that from you. I mean, we thought about that, and we just believe nobody will ever buy that argument that our grammar can decide for the community what's grammatical or not. I mean, that's...
Well, yeah, I mean, its benefit is that it's more restrictive than these tree bank grammars, so that it, and that might be something you can leverage. Unfortunately, it rules out evaluating your own system. Yeah. But it would be something interesting just to take the output of a range and see if you can't get something that correlates. And maybe you'd need something that's a little finer, like how badly did it crash?
Yeah.
You know, something that just needed a small number of repairs presumably would be more fluent than something that needed a ton of repairs. Yeah,
that's another way to do. I mean, this. I mean, people have been working on parsing. Repairs. How many repairs do you need to get to repair the? And you can divide repairing grammaticality from repairing translational adequacy, in our case, very easily. I mean, it's really...
So do you think that would be something that would be worthwhile?
I think so.
And it doesn't matter what the community thinks. I mean, I'm not joking, I'm absolutely serious. I mean, there's no doubt that it would be worthwhile to write an article and publish it about what the point of view is, what the results are from Brian's point of view. And the fact that the world would not accept it everywhere, that is irrelevant. It's an interesting piece of news about a particular machine translation technique.
So would you feel the same way if the system was evaluated by a parser based on the tree bank grammar?
Yeah, I mean, I think there are all sorts of articles which are not worth reading at all, right? And this one is worth reading.
The tree bank grammar will, well, if it's well smoothed, then it will parse modern standard Arabic, right? Even if it's trained on English, it'll assign unknown word categories and it'll come up with an analysis.
My point is that way it'll be a stochastic, a parse with a score.
Well, that's true. Yeah, so you would get a score out of it. But you could do the same.
Yeah.
You could do the same.
Okay.
Na, mám čas.